Can visual pre-training enable data-efficient robotic manipulation? Towards answering this question, we propose R3M, a universal visual representation for robot manipulation. Consider the standard robot learning pipeline. Suppose I want to train my robot to fold my towel. Normally, I would begin by collecting demonstrations, then training and deploying a policy end-to-end from images. However, chances are this won't work out of the box and likely would require a large amount of demonstrations before performing effectively, placing a significant burden on the human supervisor. Can pre-training make learning such a robotic manipulation skill more data efficient? Indeed, other fields in machine learning like computer vision or NLP have been able to mitigate this issue through pre-trained reusable representations. In these areas, training with scalable objectives like self-supervised or cheaply supervised learning on massive, diverse datasets has produced representations reusable for a wide range of downstream tasks, making downstream learning more efficient. Thinking back to our towel folding robot, our life would be much easier if we could simply download a pre-trained representation, collect just a few demonstrations, and learn a good policy on top of the fixed representation. In this work, we aim to make this a reality. Towards pre-training a visual representation for robotic manipulation, we're faced with two key questions. What is the right data to pre-train on for robotics? And what is the right objective to produce good representations for robotic manipulation? On the side of the data, we know that we need large and diverse data sets, and ideally, data that involves real-world interaction, as this is what we seek from our robots. Thus, a natural choice for pre-training data is diverse in-the-wild human video datasets, which contain diverse real-world interaction paired with natural language. Towards the right training objective, we hypothesize that a good representation for robotic manipulation contains three components. First, its features should capture temporal dynamics, as any robot using the representation must sequentially interact in its environment. Second, it should capture features predictive of language, which informs what parts of an image or video are relevant to the task at hand. And finally, to enable data-efficient downstream learning, it should be sparse and compact. Concretely, we propose R3M, Reusable Representations for Robotic Manipulation. We begin with Ego4D video data paired with natural language. We train R3M with time contrastive learning, encouraging images closer in time to be closer in embedding space. With language video alignment, encouraging R3M features to be predictive of whether video and language annotations match. And finally, with an L1 sparsity penalty. Using R3M, we're able to efficiently learn a wide range of robotic manipulation tasks in both real and simulated domains. First, does R3M enable efficient imitation learning on unseen environments and tasks? Second, which components of R3M are important? Third, how does performance vary across viewpoints and demo dataset sizes? And most importantly, can R3M enable data-efficient learning in real-world environments? Our evaluation focuses on low data imitation learning from pixels, where an MLP policy is trained on top of a fixed visual representation. We consider 3 environments with 12 tasks total, 5 from MetaWorld, 5 from the Franca Kitchen environment, and 2 from the Adroit hand manipulation suite. Each environment is also evaluated over 3 camera viewpoints. In our first experiment, we compare R3M and comparisons on Franca Kitchen, MetaWorld, and Adroit environments, and see that across all domains, R3M achieves a 58% success rate on average, despite never being trained on data from the target environments or tasks. We additionally observed that R3M enables over a 10% improvement in success rate over existing visual representations like CLIP, MoCo, and supervised ImageNet, which have been found to be effective for learning control. Finally, we see that R3M is significantly more effective than learning from scratch, improving success rate by over 20%. In our second experiment, we see that removing different components of R3M like random cropping or the L1 penalty hurt performance. Performance on the Franca Kitchen and MetaWorld environments is especially impacted by removing the L1 penalty. Removing the language supervision from R3M has the greatest negative impact on performance, especially on the Adroit environments. However, even without language, the fully self-supervised version of R3M still achieves a 50% success rate, still higher than using existing pre-trained representations. In our third experiment, we see that the performance improvement from R3M is consistent across all viewpoints for each environment. And moreover, we see that as we increase the number of demonstrations, the performance improvement from R3M is largely consistent. Finally, we study how R3M enables efficient learning in a real-world environment. We take a Franca Amica Panda robot into a real graduate student apartment, and using less than 10 minutes of demonstrations per task, learn tasks like putting the lettuce in the pan, pushing the mug to the goal, closing the drawer, putting the mask in the dresser, and folding the towel. In total, R3M succeeds 56% of the time on these tasks, almost double the success rate of using clip. Overall, our experiments suggest R3M can be used off the shelf for data-efficient robotic manipulation in visually rich real-world environments. R3M can be added to an existing robot learning stack with just a few lines of code, and code and pre-trained models are available at the links below.